Can everybody hear me? Oh, great. Oh, that's loud. Hi, well, thank you so much for that intro. I'm really happy to be here. This is sort of an honor for me. I kind of changed careers about 9 months ago when I joined Clara. I was working on device drivers in C, video graphics, for years. And I decided it was time for a change of pace. And here I am talking to you about Spark. So this is super exciting. I've chatted with a few of you so far about your experiences with big data, with Spark, with Hadoop, with what you're looking for, what you're looking to learn, where you are now, and you're sort of all over the place. So, and that's great, and that's a great audience. I hope that you'll all learn something from tonight's talk, and if you have any questions at all or want to learn more about Clara or Spark or whatever you want, please chat with me afterwards. I'll be happy to chat with you some more. If you happen to have, I forget how much the tickets are, they're kind of pricey, but there is a Spark Summit coming up in Boston, Massachusetts, the second week of February. So if this is too warm for you, if you feel like freezing, if you'd like to go to your local RAI and give them some business buying those down coats that nobody buys, there will be a Spark Summit in Boston, and it'll be a great event. I've been to one in San Francisco, and a lot of the community comes and gives a lot of great talks there. So I'll be giving a version of this talk at the Spark Summit. If you're curious, check online around the beginning of March. They do record and broadcast the talks. So I think a version of this talk will be online. And of course, this is being recorded too. So if you missed anything I said and you need to leave and can't ask me later, it's all on the record. Let's get started. All right. Let's see if this thing is working. They gave me a lot of toys today. This is a laser, apparently, and a pointer. Neat. So who am I? Again, I'm a software engineer at Clara, focused on Apache Spark. And I'm also a Spark contributor. I've made a couple of documentation changes, and I've got 2 major-ish patches waiting in the wings. I really just need to stop working on this talk and go answer some code reviews to get them in. But it's a neat project. It's a good community. And I guess compared to a lot of my colleagues, I've sort of come up the stack to Spark. A lot of my colleagues are former application developers or systems administrators or something like that, and they've sort of come down the stack to Spark, this distributed computing platform that's all the rage these days, whereas I've been looking up from the kernel level to it and saying, oh, this is kind of neat. Let's look at what's giving us all these strange syscalls. So I've got a unique view, I guess, compared to some of my colleagues. I've also kind of been a long-time student of distributed systems, and there are a lot of lessons from distributed systems that we learn that kind of keep repeating themselves over the years as we go from system to system to system, and we're seeing some of them in Spark as well. And about me, I've lived in Austin for about 3 years. I'm really excited to be part of the big data and Spark communities here. I've lived in, New York and Boston and the Bay Area, and I like Austin the best, so let's keep it awesome. All right, so why does Clara care about fault tolerance? At Clara, we're a big data company. Big means terabytes, tens of terabytes, hundreds of terabytes of data. In fact, during one of my interviews for my job, one of my VPs, Anupam, some of my Clara colleagues might know him, asked me to try to contrive an example that could be interesting for a Clara use case. And I came up with Austin Energy. I said, okay, if everybody's got a smart meter, and that smart meter is giving data every second or so, what sort of a computation platform would you need to be able to crunch all that data in real time to give analytics and to tell the power company when they need to power on a generator or shut some things down? And that's a pretty interesting use case, and that's an example of a pretty big data flow. Something else would be a real-time map application or something like Facebook. They definitely are Spark contributors. But we're a big data company. We support big customers running big applications on big hardware. Everything's big. I mean, if any of you have played Super Mario World 3, Mario Brothers 3 rather, on the NES, World 4, everything is big. That's how I think of it. You've got these big clouds. You've got a tiny little Mario over there, big clouds. But big can mean $1 billion a year in business. It can mean core business logic. It can mean 1,000+ node clusters. That's why people love Spark. You can play with it on your laptop, and then you can go run on a 2,000 node cluster. I'm sure Amazon will love it if you do that, because apparently I did a little calculation. An 1,000 node M4 4x large EC2 cluster, just sitting there doing nothing, burns $958 an hour. Now, if you go over to Austin Executive Airport and you have a pilot's license, you have to be certified and all this stuff. If you just want to take out a little twin-engine jet, and fly it around yourself. It'll cost you about that much. So I like that example just because outages are a big deal. We take them very seriously, and if your application goes south, your 1,000-node cluster is just sitting there burning energy. It's like your little jet just sitting there on the runway with the engines going, not doing anything. And that's the cost just to sit there. Let's not forget, oh yeah, there's really important business logic on top of this, and we're losing money every second that our application's not running. So we take fault tolerance really seriously, and we're all working to make Spark as fault tolerant as possible. So given that this is a mixed audience, I want to talk about some basics of what fault tolerance is in Spark before we go too much further. I'm going to kind of jump into this pretty quickly. I'm happy to answer questions after the talk, but we will. I guarantee you I'll give you enough information to follow along with the case study that's going to come up pretty soon. So let's talk about the basics of fault tolerance. So Spark itself was Matei Zaharia's PhD thesis, and he founded a company out of it, and it's taken off wildly. And it was designed to be fault tolerant from the very start. It's designed to also take the ideas of MapReduce and just make it faster. So the primitive of operation in Spark is this thing called an RDD, or a Resilient Distributed Data Set. You'll see this all the time in Spark literature. It means multiple pieces of data and multiple copies. So in this example here, if you see this little black dotted line right under stage 1, there are 4 blue boxes. Well, those blue boxes together, their union would be an RDD. So for example, let's say that you have a data set that consists of pictures of every Amazon employee. And let's say that you want to run some computation that tells you how many of them are wearing glasses. And then you want to merge that calculation with how many of them are also wearing hats. So your RDD would be this collection of all the pictures. And specifically it would be, let's take these, how big is Amazon? Let's say 10,000 people. That's probably too small, but order of 10,000. Let's take these 10,000 images, let's break them up into chunks, let's duplicate these chunks on multiple machines, and now you've got a whole bunch of machines, each with a chunk of those pictures. And now when you run calculations or computations, they all run in parallel on separate chunks of data. So for example, stage 1 will take those 4 chunks of RDD, map them to 4 chunks of RDD. So for example, you might have as an input everybody's picture, and the output is, are they wearing glasses? A yes or a no. So the fault tolerance really comes from the fact that there are those multiple copies. It also comes from the fact that there's something called lineage, which means that for every RDD operation, we know the steps that we took to get there. So if a part of the RDD goes south, if you're on a machine that, if there's a chunk of that RDD that's on a machine that gets destroyed and there are no other copies, we know that we started with this first data set, we did this operation, and if we need to, we can go back and we can fetch that original copy. We can do those operations and we can build back up to where we were. Sure. So on top of that, HDFS or HBase or whatever data store Spark itself is using offers its own fault tolerance primitives. So to some extent, we get some fault tolerance from the layers that Spark builds on for free. So to be clear, a lot of these things that I'm talking about here, these stages and stages in this diagram, are in memory. With MapReduce, it's a very straightforward, simple, fixed pipeline. Map, reduce, and we're forgetting a write to disk. Map, reduce, write to disk. Map, reduce, write to disk. It turns out that with a lot of data flows that people really care about, that write to disk step takes a really long time because disks are really slow and computers, CPUs, are really fast. So if anyone here is at Intel or whatever, thank you for making that fast. But because you're doing all of these things in memory, we now need a way of being able to execute reliably when we're not touching the disk as often. So instead of map reduce disk, we might do something like map reduce disk. Or we might do 1,000 operations before we write to disk. So we need that ability to regenerate lost data. We need that ability to detect lost things. We need that ability to replicate. So This is where we start to go into some more details. This is the API level fault tolerance that Spark gives you, this RDD, and this this sort of transparent view of a Scala collection as something that distributes over a cluster. That has to be implemented somewhere. So Spark itself is, of course, a collection of modules like the scheduler and a bunch of other things that actually make your application run. And the scheduler is where I spend a lot of time. That's it's analogous to the scheduler in a kernel or any other job submission system. It's something that figures out what work needs to be done. It's something that figures out what resources are available to do it and maps that work to be done to resources and make sure it actually finishes. It keeps running down the line. So the scheduler is a core piece of Spark code that has the responsibility of actually executing all of your work on these different nodes. And there are a few features that we'll be talking about in the context of this fault tolerance talk. There is something called the Blacklist, which means that the scheduler itself can decide that a particular execution resource is not fit for execution and therefore won't give it work. Another thing is this idea of not only duplication, but also of locality. So the scheduler, when it's assigning work, will try to figure out what nodes in your cluster already have the data you need to achieve the answer that you're looking for, to do the work that you've got assigned. And it will preferentially try to give that work to a cluster node that already has all the data there, because then it saves some network traffic and hopefully your job will go faster. Fine. So these are some of the basics. But of course, in production and at scale, we learn a few different things. So this is a slide that makes me laugh a little bit. One of our coworkers is, as a hobby, sort of a commercial barbecue chef, and goes to cookouts and competitions where he'll make thousands of racks of ribs for thousands of people. So we chatted a little bit about the differences between me running one little smoker in my backyard and versus him buying meat by the truckload and doing all of these things. And you find different issues in production and at scale. And that's really what I'm here to tell you about tonight. It's really two issues, but we'll be focusing on one of them, where we're talking about fault tolerance, but in production and at scale. So these are real customers that we've got. These are real applications that we're trying to run. We unfortunately can't divulge too many details, but rest assured, these are things that you probably want running. We certainly want them running. Okay, so with that, let's start on our first case study. Now, this is really the meat of the presentation. We'll be talking about this issue that we on the Spark team have been kind of wrestling with since probably April of last year. And we've finally brought it to resolution. It's been a long road, and you'll sort of see why that is. But the issue is called Spark 8425. If you go to the Apache Jira page, you can follow along if you'd like to, if you want to just cut to the chase and read along for yourself. But it's a real-world example of a customer encountering a concrete fault tolerance issue within Spark, something that was not covered by any of the other assumptions that we've got. And it was really fascinating to work through it and to see what assumptions were there. So let's dive into it. So on April 22nd of 2016, at about 3:30 p.m. Eastern Time, a customer reports an application failure. They've got a Spark cluster. It's their own Spark cluster, by the way. It's some important thing where they need the data in-house. They've got hundreds of nodes. They've got 8 disks per node. So I think I was chatting with some people at Dell or whatever. These are racks and racks and racks of pretty beefy multi-core, multi-disk nodes. I mean, this is an expensive cluster, $1,000 an hour or something to run it. The application's running on this customer Spark cluster, and high availability is critical for this application. And as soon as we found out about this issue, the customer contacted customer support contacted engineering. We got on a WebEx call with them. We walked through the exact issue. We got their cluster back up, and I think they experienced a total of two hours of downtime. That doesn't sound like a lot, but it's 2 hours in the middle of the week, in the middle of the day, in an application that lots of people are using for lots of important things. It's not ideal. Some VPs at this company were pretty upset. So we were charged, the Spark team, with figuring out what happened. So we resolved to root cause the issue and make certain it could no longer happen. So the immediate cause, or at least, cause is not the right word. The immediate symptom was a file not found exception. The entire application crashed because of a file not found exception. Something that you'd think should be pretty well handled. I mean, multiple disks, multiple machines, but file not found exception. So what we found was that one of the systems had one disk that was failing. Not failed, but failing. You know, maybe if you'd looked at smart data, you could see that the health is not great. Maybe if you'd run some metrics on reading and writing, you could see that it was taking a really long time to return. Maybe there could have been some other heuristic, but the fact is we had one disk and the application failed. That's pretty much what we knew on April 22nd. So again, RAID could have corrected it, but that's all kind of irrelevant. What's relevant is that that due to some interesting conditions in scheduling logic, work continued to be assigned to a node with a bad disk, eventually causing the entire application to stop. So particularly damning is this comment that the customer made. HDFS and Yarn responded to the disk failure appropriately, but Spark continued to access the failed disk. So it seems like some other parts of our environment here knew that the disk was bad, knew to leave it alone, but Spark was still hammering it. So that's sort of unfortunate. Yarn, by the way, is, I don't think I introduced it before, so it's called the cluster manager. So Spark runs on top of Yarn. It can also run on top of Mesos. These are services that are the interface between Spark and the actual cluster itself, and an intermediary for scheduling. The Spark scheduler talks to Yarn quite a lot. And HDFS is the file system. So the computation engine is still accessing this bad disk, even though the file system and the resource manager know to leave it alone. So let's dig further to see what was really going on here. All right. So we spent some time looking at log files. We spent some time trying to reproduce the issue ourselves. And reproduction is really critical for a bug like this because you need to be able to control all the variables while you work through what the root cause could possibly be. So we know that one node has one bad disk. And we know that tasks sometimes fail on this node, and tasks consistently fail if they hit this disk. So a task is a unit of execution. It's a single map operation, a single reduce operation, a single fold operation, what have you. So tasks succeeded if they are scheduled on other nodes. So what we found was that one disk was on its last legs, and everything would fail there. So Spark is fault tolerant, and Spark will soldier on. That's what we expect. That's what they told us. They said Spark is fault tolerant. You know, when a disk goes bad, when a node goes bad, everything will keep working, and that's not what we're seeing. So let's think a little bit more about what's going on here. So in Spark, when a task fails, it gets retried. So in order to minimize network and disk traffic, as I said before, the scheduler will preferentially retry this job on a node that already has the data that the task needs, and maybe also has some spare capacity. So here's where we're in this weird state. We have this task. We have this one executor, this one host, this one computer. It's trying to do some computation. It's accessing data on this bad disk. It fails. The scheduler is smart enough to see that it failed, and it tries to reschedule the task. And it sees, oh, hey, here's a machine that has all the data we need, and some spare capacity. Let's just give it to that machine again. Hits the same disk again, hits the same disk again, and after a certain number of failures, Spark just kills the application. So sort of an edge case. So again, I assure you, there is quite a lot of support in Spark for fault tolerance. If you were thinking about using Spark for your business logic or whatever, don't discredit it yet. I assure you, it's quite good. In fact, I assure you this issue is fixed. But at least at this time, here's the situation. Spark can handle an unreachable node. If a computation host doesn't respond to pings, the scheduler says, okay, this is no good, let's move the work elsewhere. It's got a great, robust mechanism for doing that. And Spark can handle a node with no usable disks. If you've got a node with a single disk that fails, or if you've got let me clarify, if you've got a node that only has one disk and that single disk fails, or if you've got a node that has multiple disks and all of those disks fail, Spark will be able to tell. It won't be able to read, it won't be able to write. Those will fail in a way that it can see, and the scheduler will know not to give it any work. So here's really what happened. These failure modes are binary. It's all or nothing. Either you can ping the machine or you can't. Either all the disks are bad or they're not. It doesn't really capture the subtlety of the fact that a machine can enter a state where if you give it a whole bunch of identical to the scheduler tasks to execute, some will succeed and some will fail. It wasn't doing something very reasonable by default in that situation. And that's terrible. That's really terrible. So this is where we start getting on the road to a fix. So Spark itself has a whole bunch of configuration variables. They're listed in the documentation, and there are a bunch that aren't in the docs at all. They're in the code. And after some experimentation, after some investigation, we recommended to the customer that they set the top two keys: Spark Scheduler Executor Task Blacklist Time and Spark Task Max Failures. So let's look at that first one, Executor Task Blacklist Time. This is a value that tells a scheduler to blacklist, to not use, an executor task combination for some amount of time. So let's say that your particular task runs on this particular executor, hits this bad disk, and fails. Spark itself will retry that task. But if it's within this executor task blacklist time, it will know to not run that task on that executor. You might get a different executor on the same node. So let's recall that a node and a host are the same thing. It's a box. Here's your host, here's your node. It can have multiple executors running on it, ideally one per CPU core. And at least this will tell it to not try that same exact executor, because that same exact executor will access the same exact disk and fail again. So at least it says, okay, try the same machine in a different configuration. Maybe try a different disk. Maybe that'll work. If it sees a success, then it just goes on. Fine. What we're trying to avoid is another failure. And we also have Spark Task Max Failures, which is another hint to the scheduler that says, okay, don't kill the application until you see this many failures. So the sort of the hack there is set that to a number that's bigger than the maximum number of executors on the node. So let's say that my little MacBook here, which has 4 CPUs, has 4 executors on it. If we set that value to 5, what'll happen is, due to locality preferences, the task will run once on each of the executors on the MacBook and fail. But then we've got one more try left. So we can try again on another host and hopefully it'll succeed. This is, it's not great. But it turned out that this was good enough to unblock the customer. It was good enough to get the VPs to stop yelling. It was good enough for the engineers to have some coffee and to think about a long-term fix. And this was a state of the art on Spark 1.6 and Spark 2.0. So here's where the fun begins. This is where the long-term fix began. This is where yeah.
There was another property down there you didn't mention. What is Spark.Speculative?
Yeah, thanks for mentioning that. I guess I didn't mention it because we didn't mention it to the customer. So Spark.Speculation is a hint to the scheduler that says, okay, if you find that all of your tasks are taking some amount of time and another one is taking really long, maybe let's try kicking it off somewhere else, because maybe there's something wrong with that executor, or maybe there's something wrong with the configuration where it's running. It's a form of speculative execution. It means this isn't done yet, let's try starting it again on somewhere else, and maybe that somewhere else will finish first. It's not awesome. It's also not really well tested, so we didn't tell the customer about it. We don't think it would have helped here, because if the disk was really slow, then maybe at the read or the write, maybe some head was, maybe some particular sector was bad, and therefore reads would have taken 5 times as long, and it would have timed out and forced speculative execution to run somewhere else, and maybe that would have worked. But we found that executor task blacklist time and max failures were doing better. So, I mean, that's another little trick in the scheduler. Yeah, thanks for mentioning that. I totally skipped over it, but not really too helpful here. So let's go take a look at at the real work here. And the real work was to overhaul the blacklist mechanism entirely. So we really like this idea of, hey, this unit of hardware is bad, this unit of execution is bad, let's not use it. Because then, as long as we can do that, we can take advantage of this really robust framework that Spark has got for making sure your job keeps running. If it knows how to deal with the fact that, oh, something is bad. If something is bad, we work around it. What we need to do is to have robust ways of indicating that something is bad. I mean, as a sysadmin sitting at a console, you can see a bunch of errors going by, and you could make that decision yourself. Although I'm not sure that, well, yeah, so in theory, on CDH at least, the Cloudera distribution of Hadoop, if you were to go into CM, the Cloudera manager, you could see that there are a bunch of issues, and you could manually take that node offline. And then Spark would still be running. Spark would say, oh, this node is offline, time to reallocate everything would be fine. But we don't want you to have to do that. As a system administrator, we don't want you to have to babysit all of your users' jobs to make sure that they all succeed. And as a Spark user, we don't want you to have to know the ins and outs of all of these different, they're basically registry keys, these configuration values, to know what knobs to tweak in what direction to maybe get your job running. Because more likely than not, you'll make things worse. There's just such a big space of configuration options. Unless you're really careful, you could end up hurting your performance instead of improving it. So we went to task fixing this in the scheduler itself, making the scheduler smarter. The scheduler is critical core code. It is the kernel of Spark. If you go to the Spark contributors guide on the Spark webpage, where it tells you how to submit patches and everything else and how to contribute, and contributors are welcome. There are lots of bugs. Please help us fix them. But it specifically has a note about the scheduler as an example of something that a newcomer should not touch. Here be dragons. It's sort of like whack-a-mole, or what I think of like applying a decal to a surface with a little air bubble. You press that air bubble down with your thumb and it just pops up somewhere else. And we're trying to get all the air bubbles out. Very frustrating. Among other things, on top of the fact that every customer's, every Spark user's different use cases hit the same scheduler code in all sorts of different configurations, it's just hard in a bunch of classic software engineering ways. It's multi-threaded, there are asynchronous requests, there's a lot of dynamism in the way that requests are coming in. It has to handle a bunch of different configurations for executors and hosts. I mean, it's just it's a nightmare. So on the Jira itself that I mentioned earlier, Spark 8425, my colleague posted this design doc, and for your convenience, I've made this little URL shortened thing, bit.do/bklist. It's I forget if it's 6 or 7 or 13 pages. This is a long PDF. And we go through these 7 scenarios one by one. And I won't belabor them too much here, but I really have this here as an example of something to show, hey, it takes some real thinking to get all this stuff correct. These are all the situations that we have to not break while we're also trying to make sure that this customer's job proceeds. Okay, so this is a little bit of an eye chart, but the reason I have this here is this is a comment that's at the top of Blacklist Tracker. One thing is, of course, we believe in comments to code that are implementing core logic and doing confusing things. But we specifically call out bad user code, many stages, and flaky executors, which is really the problem that I'm talking about here, a bad disk, in the scheduler code itself. So if you'd like, of course, you can pull top of tree Spark and take a look at what that is for yourself, and maybe learn Scala along the way like I did. But we have to think about thread safety while also thinking about all these issues here. So here's what we come to in Spark 2. This is checked in, by the way. The development cycle took about June through December of 2016. There are about 2 or 3 core scheduling logic experts outside of Cloudera that were really active in code review. I mean, this maybe went through 10 or 15 or 20 different revisions before we checked it in. All the usual nitty-gritty of code reviews, typos and variable renames and this and that. On top of all the correctness issues, on top of having to write unit tests for the upstream project itself to test all of these things, figuring out how to test this, figuring out what was meaningful to test. And also, one of Cloudera's, I guess, open secrets is that we have our own internal testing framework. So the unit tests on the Spark project assert correctness, but we have our own way of building clusters, of running jobs, of making sure that things are working okay. So we have our own internal test that exercises pretty well. So what we came up with is the Spark Blacklist enabled configuration flag, which is set to false for now, only because, again, the scheduler is core logic. We don't want to introduce a big change to a lot of customers that'll change everything. And Databricks and all of our collaborators agree. So it's set to false by default. If you'd like to try it out, set it to true. And then spin up a Spark cluster and go and remove a disk and see what happens. Everything should be fine. So we have these 4 configuration keys below that with their default values in parentheses. We have max task attempts per executor, default to 1. If it fails, don't try it on that executor again. Max task attempts per node, default 2. If we have 2 failures on that node, forget about it. Try another node. Move on. Max failed tasks per executor, 2. And max failed executors per node, 2. Just as they say. So the idea here is that we fail fast. If we see a failure, just scrap it. Just move on to some other node. And it is for some amount of time, which is in the code somewhere. I can't remember it off the top of my head, and I couldn't find it in time for the slides. But it's there. I think it's 5 minutes or something, and that's enough time to go and maybe kill the executor and try again. Maybe some other component will figure out that something is bad or recover from some error. Maybe some administrator will figure out that, hey, a disk needs swapping. But I mean, just statistically, if you look at hard disks, they follow this sort of bathtub curve of a lot of failures in the beginning, a lot of failures in the end of their life cycle, and relatively few failures in the middle. But when you have a 100 node cluster with 8 disks a node, that is 800 disks. So you tend to have a disk failure every week or 2. And this is just a part of running a 100 node cluster. So this happens all the time. So there are admins who are looking for disk failures, and they're going to change the disks out on you. But that's really what we came to. The part that I was working on, of course, I was helping with code reviews. I was helping write some of these unit tests and all these other things. But I worked on the UI. So in Spark itself, there's a pretty robust web UI that allows you to see the state of your cluster and see what's going on. And forgive me if this is difficult to see, but what I've added is in the executors top level tab, there's you can list all the active, dead, and total executors, and you can count the number that are blacklisted. So in this little toy example that I've contrived, I had 5 total executors, and I managed to blacklist 2 of them by doing something terrible. And you can see it broken out per executor. You can see that the driver and executors 1, 0 through 3 are present, but executor 0 and 2 are blacklisted. So at least as a user, you no longer have to sift through log files. You can now at least go to the UI, and it'll give you some hint of what's going on. And analogously, Spark has JSON connectors, so if you want to write your own UI on top of it or something like that, you can get the state that would be available in the UI that way, and there are JSON serializations of this blacklisted state. So pretty neat. I mean, we hit this really strange edge condition. We worked to figure it out, and we have this fixed. All right, so this is my second case study, and we'll go through this one pretty quickly. Yeah, go ahead. Let me hand you the mic so that you're recorded, and also so everyone can hear you.
So when you say that executor or the node is blacklisted, like how long it is blacklisted? Is it throughout the life cycle of the application, or it remains as a blacklisted for a certain period of time, and the name node will recover it after some time? But how long it is?
Yeah, I believe by default it's 5 minutes, and if the application dies before then I think the blacklisting dies with the application, and the application itself, the next time it's run will be blacklisting it again. But we are in a situation here where we expect applications to be long-lived. We expect this application that's running on the cluster to be a service that's running to provide data to other things. It's implementing some RESTful API or something that other clients need. So again, by default, I believe it's 5 minutes. I'd have to check the code. I think that's configurable as well, but yeah.
Is it not fed to any other system that the node is recovered, because it might keep failing on the same day? Every day when the same job executes again and again, it may keep failing, and it will.
Right. So the question was like, what's done with that, with the information that it's failed? I don't think anything is. It'll appear in log files. So the log file will say this executor was blacklisted for this task for this reason. And then if you've got some reporting that's looking through log files and alerting you when it sees that, then you can take action on it. But by default, it just spits out a log message. It's relatively policy-free. I mean, that's true of the rest of Spark. It's not going to send you an email or something when something happens, but you can do whatever you want with the logs. Any more questions? Okay. Oh, we're at a good stopping point, so I'll take some more questions. Sure. Yeah.
Did you guys consider doing any randomization of failures? Because obviously disk failures, 8,000, you just look at the statistics, they're going to be there for sure.
Mm-hmm.
And in fact, single failures, multiple failures, distributed failures across nodes, all at the same time are well within a realm of possibility for
Sure
a large
thing.
system.
Sure thing. So let me repeat the question to make sure I understand. I'm gonna kind of turn the question into what I want it to be, unfortunately, which is, can you tell me a little bit about what sort of fault simulations you do? And we do some. We don't do enough, perhaps, and maybe we could have caught this, but you're absolutely right. There are ways to simulate bad disks. There are ways to simulate bad network connections. There are ways to simulate bad hosts. That you can have this fun thing called a Byzantine fault, where something is intentionally giving wrong information to pretend that it's functioning well, so you can have like a compromised system. We've got a framework where it's sort of in the early stages. I mean, I think that working on this bug really reminded us at Clara that this is something that we need to spend more time on. But our engineering team's not huge, so we have to sort of pick and choose what we do work on. But yeah, we are working to do that. There's also fuzzing. There's a pretty robust ecosystem of all sorts of ways that you can try to break a system. And we've got a little framework that does that. We're starting to head in that direction. We don't have a whole lot yet, but we are. We're finding bugs as we go with customers reporting them with code inspections. So yeah, we would find more things that way, but we're not doing a whole lot at the moment. But we should, and we know, and we're working on it. Does that answer?
Sort of.
Sorry. Then let me try that one again. How can I better answer that one?
I don't know if you can do a better answer. It's just that it's a prioritization sometimes, and sometimes it's a starting of the architecture, right? It's much easier to architect in the ability to kill things selectively and then put in hooks later on to activate those, to simulate those failures, than to go in 2 years later and try to do that, right? Because just putting in the hook to emulate a disk fail might break something else.
Yeah.
Right.
Yeah. Well, I guess some of the implementation details of the system we've got, it doesn't really hook into what's running. It's an interposer. So, for example, it'll position itself between Spark and the I/O layer. It'll run on the system itself. So we've got sort of an instrumented system that's able to do these things outside of Spark. But instrumentation within Spark itself, we have something like that for our internal testing. I don't think we're quite using it for fault injection in the way you described. The thing I'm thinking of is really outside of Spark. But the other thing is, if we're going to add hooks like that, I mean, it's an open source project, so we have to convince a community that it's worth having, that it's not going to break other things. The community has been extremely conservative when it comes to adopting scheduler changes. So that would be maybe something we can implement, but it'd be difficult. So we work on our own solutions. I think in the long run, as community members, we would like to contribute back to the Apache Spark project's testing infrastructure. So maybe we'll see better testing upstream in the future. But that's, again, we've only got so much we can do. Great. Any more questions? Sure. Go.
So if I have a AWS cluster and I'm actually dynamically spinning up a cluster based on an application, so are these properties, can I set these properties dynamically in my application code?
Sure.
And also handle the checkpoints in case any executor fails, any job fails during the on a node, and I just want to recover from that point of failure to the.
Sure. Yeah, you can do that. You can configure checkpointing settings. We try to recommend against using it for starting and stopping jobs to save state, but for what you're describing, recovering from failure, that would be appropriate. All the keys that I described, so let's go back a moment to these. All of these are per application. It's per instance of Spark submit or for the entire lifetime of a Spark shell. So I don't know what sort of environment you're using to launch your jobs, but you will need to specify them either. So for example, in Clara Manager, in the cluster manager itself, you can define these as global defaults, and then when you spin up or tear down individual nodes, Spark will appear with these configuration values set. So you'll have to, again, I don't know the details of your setup, but however else you're configuring Spark as is, you'll need to pass these in. So like, just as an example, I tend to keep a little shell script that I use to launch my Spark shells when I'm doing testing, and those will tend to contain 50 different parameters that I'm setting, and I'll just run it through that. But the defaults are in parens, and the hope is that the defaults are good for everybody. Question?
So, do you have
Here you
any recommended, from a data center monitoring perspective, application monitoring, any monitoring frameworks like Zabbix or things like that with Spark?
I'm a little biased, but
For
we do
such
issues. Clara Manager. I unfortunately, I'm personally not too familiar with the other frameworks that are out there, but I mean, they're generating log files, so whatever it is that you use, as long as it's able to read log files and take action on them. Just parsing free text data or JSON is a pretty well solved problem. So, no, I don't have any specific recommendations. I wish I did. It's something I'd like to play with at some point. I just haven't gotten to it. Yeah.
Well, I have a question for the, not directly for the schedule itself, but it's about the side effects of the failed task. So one example is accumulate in the Spark, for example, or even extend that to the Hadoop matrix. So one of the shortcomings of the Spark is that there's no nice way, like in the MapReduce job account, you're able to track a global kind of information.
Right.
And also the things get even more painful in that if the task fails, you will not automatically roll back the contribute. So that's something I'm not sure if it's on the plan to get that rollback, essentially. Even probably starting with the Spark accumulate as a starting point, or even extend it to the global, like including the Hadoop metrics.
Yeah, the accumulator issue is something that we've heard about from customers too. We're working on it. The most offensive thing that Spark can do is to wait for certain until all the tasks are done before completing, and assert correctness. And your hope is to get these exactly one semantics from every task in every stage. And if you don't, then your accumulators are going to be all wrong, and we don't really have a way of checkpointing as regularly. So that's something we're working on. That matters a lot for the streaming use case as well. So when you've got some stream in. That's sort of an open problem, unfortunately. It's something we know about. It's something we're working on. That is certainly something that we will upstream when we make some progress on it. I don't know if I have anything else meaningful to say about it at the moment, other than it's frustrating. And in that case, maybe checkpointing will help you, because you'll know that you were at a previous state and you can start again from a previous state. But It's not something that I've personally investigated a whole lot with these set of patches either, so I can't really say yes it works or no it doesn't. But again, knowing nothing else and just being conservative, if you don't have exactly one semantics in one way or another, your accumulators are going to be garbage. Hopefully they're not. Okay, so I'll zip through this case study here. This is another very real bug, Spark 4105, that a lot of our customers were seeing. It's really noteworthy because it's been open since November of 2014 and was only closed maybe a couple of weeks ago. And it's non-deterministic. It was a really difficult bug to figure out. So let's go back to this wonderful diagram here we've got of the Spark architecture. Let's focus in particular on these yellow arrows. This is what's called a shuffle, which is a many-to-many operation which happens when you decide to repartition an RDD And maybe it's because you've finished one stage of computation and now you need to redistribute all the data to get all the information to the right locations for the next stage. So this, as you can imagine, uses a ton of network bandwidth. You've got this huge many-to-many operation. Everybody's talking to everybody. So Spark tries to be pretty conservative with network bandwidth here. It'll do some compression, and it'll also use some torrent broadcasting based on BitTorrent to try to be as efficient as possible. But we are finding a whole bunch of failed to uncompress errors, which would kill applications. And customers would just run into this every now and then. We didn't really know what to tell them. So what ended up being the issue, and again, I don't fully know the details of what the root cause was. I'm not sure anybody does. But what was happening is that some blocks of compressed data themselves were corrupt. They'd have corrupt headers or a wrong bit or something. They wouldn't decompress correctly. But instead of some component in Spark catching that exception and preventing it from taking down the whole application would just fall down. So I guess it took a long time to get that checked in because it's difficult to reproduce. So the solution for now is to check within Spark to see if individual chunks of broadcast data are corrupt, and then to ask for them to be rebroadcast instead of killing the whole application. Again, we're sort of playing whack-a-mole here with issues that'll cause application failures. So sorry, again, it's a little hand-wavy. It's a bug that I'm still investigating, and we're also kind of running a little lower on time than I'd like, so we're gonna not spend too much time on that one. It's also not so interesting because I didn't work on it, I guess. Well, not so interesting to me. So what did we learn? That the Spark scheduler is responsible for assigning units of work to compute resources. It's the back end for a lot of the fault tolerance features that we talk about. It's where the rubber meets the road when it comes to fault tolerance. There are a few knobs to tweak. We've talked about some of them. There are more. They're in the documentation. Hopefully you don't need to know about them. You're welcome to read about them. I just find them fascinating for their own sake. And other things can fail besides the scheduler as well. We very briefly looked at that shuffle fetch failure. The main thing that has been clear to me in my work is that many classical distributed systems problems are still present. There's a very robust literature of distributed systems research that dates back 20, 30 plus years, and we're hitting a lot of the same issues over and over again. It's part of Spark growing. It's a very active project. A lot of people are looking at it. A lot of people are contributing to it. It's growing very quickly. It's getting the attention, hopefully, of some folks who have spent some time looking at distributed systems. I mean, the folks who wrote it are experts in them, but again, these issues tend to come about in production. So some recommendations for application developers. Still working to figure out what some better ones might be, but for now we've got gather and read your logs early and often, set some expectations, grow slowly, start with one executor and one host, especially if you're looking at performance. Make it a scientific process. If you add more resources, think about how that's going to affect your performance. Think about how you want it to, see what it does, see if that's what you expect. Don't just take your critical job, run it on the big cluster, hope that it's going to run perfectly, and hope that you can go home. We're not quite there. I think that oftentimes that will work, but certainly grow slowly so that you understand what's going on. And that's about it. So thank you so much. I'll be here for a little bit. I can answer any questions now or when you want. And my email is jose@clara.com. So again, it's been an honor to chat with you, and thanks for listening.